What's up, Skywatchers? What is up indeed? Friday, December 19th, 2025. Today we're going to talk about the atmospheric river that slammed the Pacific Northwest, aerosols, electromagnetic radiation, and what's happening at the jet stream altitude where the weather is shaped long before the rain ever falls. Alright, let's get into it. In mid-December 2025, a powerful multi-phase storm system struck the Pacific Northwest, producing one of the most destructive weather sequences the region has experienced in years. The event unfolded over more than a week and combined record-breaking rainfall, widespread flooding, and subsequent hurricane-force windstorms that impacted Washington, Oregon, Idaho, Montana, and even Colorado. From December 8th through the 11th, relentless rain caused rivers across western Washington to surge to record levels. Olympia recorded over 3 inches of rain in a single day, while parts of the Olympic Peninsula received nearly 17 inches over the 3-day period. Rivers including the Skagit, Snohomish, Cedar, Nooksack, and Green exceeded flood stage, with levee breaches reported in King County communities. Tens of thousands of residents were placed under evacuation orders, and landslides and washouts closed major highways and forest roads. Then came the second wave of heavy precipitation that arrived on December 14th through the 16th, further overwhelming the region. Snow levels rose above 7,000 feet, triggering rapid snowmelt and immediate runoff to already saturated river systems. Flooding intensified across Washington and Oregon, while northwestern Montana experienced significant rainfall and flooding, prompting disaster declarations in Lincoln, Sanders, and Flathead counties. On December 17th and 18th, the system escalated into a destructive windstorm, delivering hurricane-force gusts across the Pacific Northwest. Peak winds reached about 142 miles an hour at Coldwater Ridge in Washington, 138 miles an hour at Mount Hood in Oregon, and over 110 miles an hour in parts of western Washington. Trees, power lines, and structures were heavily damaged. Roads were blocked and semi-trucks were blown over on major corridors, including I-90. At peak impact, power outages across the region exceeded 500,000 customers, with hundreds of thousands affected over the course of the storm. Restoration efforts were complicated by flooded infrastructure, ongoing landslide risks, and additional storms approaching before recovery could be completed. The storm resulted in confirmed fatalities from flooding and falling trees, serious injuries, widespread infrastructure damage, and prolonged disruption across multiple states. As emergency crews worked to stabilize conditions, forecasts warned of additional rain systems threatening further flooding, underscoring the prolonged and compounding nature of the event. Alright, let's talk about aerosols, electromagnetic radiation, and weather modification at jet stream altitudes. Everything discussed here operates within established atmospheric physics, cloud microphysics, radiative transfer, and electromagnetic science. The focus is a narrow and physically constrained scenario, altitudes between 30,000 and 43,000 feet. The mechanism that we're looking at is repeated high-altitude aerosol deployment in the upper troposphere and lower stratosphere interface, and there is an additional variable, the electromagnetic radiation, interacting with the system. This altitude range is not theoretical. It corresponds to the cruising band where aircraft routinely operate and where persistent aerosol trails are observed forming, spreading, and evolving under upper-level winds. Between 30,000 and 43,000 feet, the atmosphere behaves differently than it does near the surface. Air density is reduced to roughly 25–40% of surface levels. Water vapor is scarce, but the ice phase processes dominate. Clouds are primarily cirrus, anvil outflows, and thin stratosform layers. Winds are fast, shared, and horizontally efficient. The global electric circuit passes directly through this layer. The region acts as an interface between surface weather and planetary scale circulation. Energy, moisture, and the electrical charge are redistributed here before they ever express themselves on the ground. What is often observed from the ground as long-lived aircraft aerosol trails, chemtrails, represents the delivery phase of a broader process. Once deployed at altitude, aerosols are no longer governed by the same rules that apply near the surface. At these heights, gravitational settling is slow, vertical mixing is limited, horizontal transport is rapid. Aerosols introduced here can travel thousands of miles, they can persist for weeks or longer, and organize into structured layers. This behavior is well documented in volcanic sulfate plumes and high-altitude wildfire smoke. The physics here doesn't change based on the source. Layering aerosols and atmospheric structure, repeated high-altitude aerosol deployment does not simply increase particle concentration, it builds the structure. Stacked aerosol layers, reinforced temperature inversions, electrical conductivity gradients. Each layer interacts differently with radiation and moisture. Layering increases residence time and stabilizes effects that would otherwise dissipate. At this altitude, aerosols primarily function as ice nucleating particles. The controlling variable is not chemistry alone, but number. Excess ice nuclei result in many small ice crystals instead of fewer large ones. Thicker, longer-lived cirrus clouds reduce precipitation efficiency. These clouds trap outgoing long-wave radiation, reflect incoming short-wave radiation, and alter vertical temperature gradients. Storm behavior below adjusts accordingly. Stratospheric aerosol injection and solar radiation modification as the outcome. Solar radiation modification describes an effect, not a single method. When high-altitude aerosols persist in the upper troposphere or lower stratosphere, they alter Earth's radiative balance by increasing reflectivity of incoming solar energy, modifying how heat is retained or released, reshaping temperature gradients that drive circulation. Whether modeled in policy literature as stratospheric aerosol injection are observed operationally through chemtrails, persistent aerosol trails, the outcome remains the same. Energy is redistributed before it reaches the surface. Weather systems do not collapse under these conditions, they reorganize. Electromagnetic radiation is not required for aerosols to influence weather. However, it introduces timing and selectivity into an otherwise passive system. The atmosphere is nonlinear. Small inputs near thresholds produce disproportionate outcomes. This altitude band lies within the main conduction pathway of the global electric circuit. It features strong vertical electric field gradients, continuous ion flow between the ionosphere and the ground, high sensitivity to conductivity changes. Aerosols naturally reduce conductivity. Electromagnetic energy modifies how that conductivity behaves. At these heights, aerosols and ice crystals readily acquire electrical charge. Particles can be polar or semipolar. Interactions respond to the electromagnetic fields. Electromagnetic radiation can influence charge separation, particle alignment, collision and agitation rates. These microphysical changes scale upward, altering cirrus thickness, cloud lifetime, and radiative balance. At this altitude, electromagnetic radiation acts through ionization rates, conductivity pathways, electrical boundary conditions. This affects cloud electrification, lightning thresholds, and ice growth behavior. The effects are subtle but persistent. When high-altitude aerosol deployment and electromagnetic influences coexist, their interaction is multiplicative. Aerosols reshape the physical environment. Electromagnetic radiation reshapes the electrical environment. Together, they influence how energy and moisture move through the atmosphere. This layer also feeds directly into jet stream dynamics, planetary wave patterns, storm track placement. Localized changes do not remain localized, and the downstream effects may include rainfall redistribution, altered storm intensity, shifts in lightning frequency, persistent cloud decks far from the source. This is how small perturbations at altitude translate into regional outcomes. Stratospheric aerosol injection represents a specific subset of high-altitude aerosol deployment. defined by altitude rather than outcome. Much of the public discussion focuses on this term because it appears in climate modeling and policy frameworks. However, many of the atmospheric effects attributed to stratospheric aerosol injection begin lower at the upper troposphere. Now let's talk about the ozone layer for just one moment. Most ozone resides higher in the stratosphere, above the altitude band discussed here, but the upper troposphere acts as a gateway feeding air, energy, and chemistry upward. At jet stream altitudes, high-altitude aerosol deployment and electromagnetic influences do not directly destroy the ozone. They increase the efficiency, duration, and reach of ozone-depleting processes while slowing natural recovery. Aerosols provide the surface for chemical reactions that activate compounds involved in ozone loss once they reach the stratosphere. Persistent cirrus alters how ultraviolet radiation propagates, affecting ozone chemistry indirectly. The result is not a collapse, it's an erosion through repetition. And at these altitudes, the weather can be modified. High-altitude aerosol deployment defines the physical environment. Electromagnetic influences shape the electrical environment. Solar radiation modification describes the outcome. Together, they can delay or intensify the storms, redirect precipitation, reshape circulation, and thin the atmosphere's margin for recovery. Alright, a huge shout out to the supporters of this channel. Thankful for using my Buy Me a Coffee link, and there was a recent contribution that was extremely generous. Thank you, Barbara Hansen. And to everyone who has chipped in through Buy Me a Coffee. This work continues because of you. Much love and many thanks. Okay, Skywatchers, stay aware, be prepared, and until next time, keep looking up.